NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve floor function equations of the form floor of x times floor of y equals k, where k is an integer. We will split into two cases, when k equals 0 and when k is not 0. Here is the general statement. We want to describe all real pairs x and y, such that the product of their floors equals k. The floor function means the greatest integer less than or equal to the argument. Case 1. When k equals 0, the product of the two integers floor of x and floor of y is 0. By the zero product property, at least one factor must be 0. So either floor of x equals 0 or floor of y equals 0. Let us visualize what floor of x equals 0 means. It means x lies from 0 inclusive up to 1 exclusive. In that branch, y is completely free and can be any real number. Symmetrically, if floor of y equals 0, then y lies from 0 to 1, and x can be any real number. Therefore, for k equals 0, there are infinitely many solutions. Either x is between 0 and 1, and y is arbitrary, or y is between 0 and 1, and x is arbitrary. Case 2. When k is not 0, the product of the two floors is a non-zero integer. That forces both floor of x and floor of y to be non-zero. We can isolate one factor to get floor of x equals k divided by floor of y. Since floors are integers, floor of y must be a divisor of k, and then floor of x is the quotient k over that divisor. For each integer pair capital X and capital Y that satisfies capital X times capital Y equals k, the real solutions come from the strips. X is between capital X and capital X plus 1, and Y is between capital Y and capital Y plus 1. Let us see this approach on a concrete example with k equals 6. Example, take k equals 6. The integer divisors of 6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. We list all pairs where floor of y equals a divisor d, and floor of x equals 6 over d. Here are all 8 integer pairs. Each card shows the corresponding strips for x and y. Any real pair inside one of these strips will satisfy floor of x times floor of y equals 6. Let us highlight the pair where floor of y equals -2. Then floor of x is 6 divided by -2, which is -3. So x goes from -3 to -2, and y goes from -2 to -1. To visualize one of these solution regions, let us draw a coordinate grid. We will highlight the rectangle for the pair equals 3, and b equals 2, which corresponds to x between 3 and 4, and y between 2 and 3. This is one of the positive factor pairs for k equals 6. To summarize the general algorithm for non-zero k. Step 1, list all integer divisors of k. Step 2, for each divisor d set floor of y equal to d and floor of x equal to k over d. Step 3, convert each integer pair into real intervals using the definition of the floor function. The union of all these strips gives the complete solution set. Final summary. When k equals 0, at least one floor is 0, producing infinitely many solutions. When k is not 0, floors are non-zero, and the floor of y must divide k. For each divisor, we get a rectangle strip of real solutions. That is the complete description for the product of floors equal to k. Example, we will solve the equation open bracket x close bracket times open bracket y close bracket equals 1. In this lesson, the square brackets mean the floor function, also called the greatest integer, less than or equal to the number. Our plan, isolate one bracket, use the fact that both brackets are integers, analyze the only possible integer cases, and finally show the solution region on the coordinate plane. Step 1. Isolate one bracket from open bracket x close bracket times open bracket y close bracket equals 1. We write open bracket x close bracket equals 1 divided by open bracket y close bracket. Step 2. Use the integer constraint. The floor of any real number is always an integer. That means open bracket x close bracket is an integer. Therefore, 1 over open bracket y close bracket must also be an integer. The only integers that divide 1 are +1 and -1. So open bracket y close bracket must be either +1 or -1. Step 3. Case 1. Open bracket y close bracket equals 1. That means y is between 1 and 2. Substituting into our isolated equation, open bracket x close bracket equals 1 divided by 1, which is 1. So x is between 1 and 2. In this case, both x and y lie in the interval from 1 inclusive to 2 exclusive. Let's visualize this on the plane. Step 4. Case 2. Open bracket y close bracket equals -1. That means y is between -1 and 0. From our isolated equation, open bracket x close bracket equals 1 divided by -1, which is -1. So x is between -1 and 0. On the plane, this corresponds to the square from -1 to 0 in both x and y. Final summary: because the floor of x and the floor of y are integers whose product is 1, the only possibilities are both equal to 1 or both equal to -1. Therefore, the solution set in the xy plane is the union of two squares. First, 1 less than or equal to x less than 2, and 1 less than or equal to y less than 2. And second, -1 less than or equal to x less than 0, and -1 less than or equal to y less than 0. Visually, the solution consists of exactly these two shaded unit squares on the integer grid. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.